For the past several weeks, we've been talking about magnetism. Magnetism causes things to attract and repel, and we quickly tried to fit magnetism into the same spooky force model that we used for gravity and electricity. This worked fairly well, but there are a few issues. Elementary particles possess mass and charge, and thus interact through gravity and electricity all the time. There is no fundamental property for magnetism. We decided that moving charge was the best way to describe magnetic property. It works, but it's a little unsatisfying. Many physicists were so put off by this that they spent their whole careers looking for fundamental magnetic particles, and they never found any. Another point of dissatisfaction with magnetism has to do with visualizing the blanket model for magnetism. In gravity and electricity, when we create a slope in the blanket, objects with the corresponding property roll downhill. With magnetism, if we have a slope in a particular direction, objects actually get pushed perpendicularly to the slope. To compensate for this, we need our object hand rule to figure out what's going on. These 2 points led people to think about magnetism differently. A breakthrough was made when we realized that magnetic property was not based on the absolute motion of the charge, but on the relative motion of the charge. You can see this in many of our demonstrations, but it might be best viewed with a PhET simulation. This magnet will interact with this coil if the magnet is moving, but it will also interact with the coil if the coil is moving. All that matters is that the agent and object are moving relative to each other. If neither one of them is moving, nothing happens. Interestingly, if they are both moving in the same way, and thus not moving relative to each other, still nothing happens. Galileo talked about relativity 300 years ago. He made some observations about relative velocity that are pretty easy to understand. Let's take a quick look at Galilean relativity with a familiar modern context. Suppose we have a black car that is going forward at 30 miles per hour. In the next lane, we have a blue car also going forward at 30 miles per hour. Up ahead, we have a tree that is not moving. The tree is green. And further up ahead, we have a red car coming toward the first 2 cars. How does every observer perceive the motion of everyone else? Let's agree that stuff moving to the right is positive and stuff moving to the left is negative. Let's organize our thoughts with a chart. We can start with the tree. The tree, of course, thinks it's not moving. When it looks at the blue car, it thinks it's moving toward the tree at 30 miles per hour. Similarly, it thinks the black car is moving toward it at 30 miles per hour. The red car is moving at 30 miles per hour, but in the other direction. Let's switch to the blue car. The blue car thinks it's not moving. This is not weird. When you're in a car that's moving, you rarely have to think about that motion. If you're sitting in the back seat and looking at your phone, you don't really have to think about the fact that your car is going 30 miles an hour. It's not moving relative to you. When someone in the blue car looks out and sees the black car next to them, they think he's not moving either because they have the same speed. Looking down the road, they think the tree is coming toward them at 30 miles an hour. When they see the red car, they think that car is coming toward them at 60 miles an hour. The black car and the blue car have the same perspective because they're traveling together. Switching to the red car, he thinks he's stationary. He thinks the tree is coming toward him at 30 miles an hour, and he thinks both cars are coming toward him at 60 miles an hour. All of this data is self-consistent, and life was good for about 200 years. Then people noticed something. If you stand on a car moving at 40 meters per second and throw a ball forward at 20 meters per second, someone standing on the ground thinks the ball is moving at 60 meters per second. That's fine. But if you stand on a car moving at 40 meters per second and shine a flashlight forward, both you and the person on the ground sees the same speed for the light. This is not a mistake. That's what happens. And it's super weird. In the 1890s, a guy named Hendrik Lorentz from the Netherlands made some progress on this by figuring out new rules for relativity. We will talk about all of these rules in great detail in our modern physics class, but for now we only need one of them. Lorentz says that when you're moving, you shrink in that direction. He called this length contraction, and it's a real phenomenon. If you measure an airplane from nose to tail when it's on the ground, you get a certain length. If you make the same measurement from the ground while the plane is moving towards you, you get a smaller value. The faster the plane is moving, the more noticeable this is. What if someone inside the plane measures the length of the plane with a ruler while the plane is on the ground? They get a certain answer. If they make the same measurement from the inside of the plane while the plane is moving, they get the same answer. That's because they and their ruler are moving at the same speed as the plane and there is no relative motion. They are effectively measuring a shorter plane with a shorter ruler, and the results match the stationary values. Again, this effect only exists in the direction of motion. If you're moving toward me, you look just as wide as ever, but smaller from front to back. Specifically, let's say I want to figure out how thick my friend is. I can do this by using radar to measure how far away their back is from me, and then measure how far their front is away from me, and subtract the difference. That will work just fine if we're both stationary. However, if I'm walking toward my friend with my radar gun, or if they're walking toward me, the signal bounces off of them and gets back to me sooner than it should have because I'm closer now. When I do my math, I compute that they are thinner. They still have all the mass they did before, but each layer of atoms that they are made of seem closer together to me. They seem more dense. How is this relevant? Let's look at some magnetism problems that we've solved recently. Here we have two parallel wires carrying currents in the same direction. We said that these two wires are magnets and will interact with each other. We can use the hand rules to see how. The top wire, as an agent, creates a magnetic field with X's on top and dots underneath them. The bottom wire, as an object in the agent's dot field, will feel a force toward the top wire. Looking at it the other way, the bottom wire is an agent creating a magnetic field with X's on top and dots below him. The top wire is an object in the agent's X field, and it feels a force toward the bottom wire. These two wires attract each other magnetically. Instead of using the hand rules, let's use relativity. Here are my two wires again. Electrons in both wires are going to the right. I'm going to draw the top electrons as blue cars and the bottom electrons as black cars. These wires are neutral, so there's one proton for every electron. Protons are stationary. They are green trees. Let's look at this situation from the perspective of electron objects in the bottom wire. They see a certain spacing in between the electrons in the agent wire. They also see a certain spacing between the trees. Since the object electrons have the same speed as the agent electrons, they seem to have the same spacing and thus the same density. However, each object electron thinks the agent trees are moving toward them. This makes them look closer together. If the object electrons think the agent protons are more dense than the agent electrons, it looks like the agent wire is net positive, and that would cause the object electrons to feel a force toward the top wire. If we think of this from the top wire's perspective, it works out similarly. Every object electron in the top wire thinks the protons in the agent wire are closer together than the electrons, and the top wire feels a force toward the bottom wire. The two wires attract each other electrically. Is this a fluke? Let's try a different scenario. This time I have two parallel wires carrying currents in opposite directions. Let's analyze this using the magnetic hand rules. The top wire, as an agent, is creating a magnetic field with X's on top and dots on the bottom. The bottom wire is an object in the agent's dot field and feels a force directed away from the top wire. The bottom wire, as an agent, is creating a magnetic field with X's on bottom and dots on top. The object wire is in the agent's dot field and feels a force directed away from the agent. These two wires repel each other magnetically. Bear with me as we look at the same situation again using relativity. The electrons in the top wire are black cars going to the right, and the electrons in the bottom wire are red cars going to the left. All the protons are stationary green trees. Object red electrons in the bottom wire see the agent trees coming toward them, which makes them look closer together. However, they also see the agent black cars coming toward them even faster. This makes them look even closer together. Therefore, the object electrons in the bottom wire think the top wire is negative, and they feel a force directed away from that wire. The object electrons in the top wire see something similar. They see the agent protons coming toward them, which makes them closer together, but they also see the agent black cars coming toward them, faster and thus closer together. The object electrons in the top wire feel a force directed away from the bottom wire. These two wires repel each other electrically. Okay, so what's my point? In physics, we talk about modeling all the time. Our job as physicists is to come up with conceptual models for how we think something works. We use simplifications and analogies to help build these conceptual models. We use data and graphs to turn these conceptual models into mathematical models that not only explain what we are seeing now, but also explain what we can expect to see in the future. When we built our electricity model, we based it heavily on analogies with our gravitational model. That worked out great. We also tried to build a magnetism model based on our gravity model. That was clunky. There was no fundamental piece of magnetism, and the hand rules are weird. Don't get me wrong, magnetism is awesome, and we understand it really well. We can build all sorts of cool toys with magnetism, like motors and speakers and televisions and computers. The magnetism model works, but it's kind of wrong. In a very real sense, there is no such thing as magnetism. What we call magnetism is really just the electricity model coupled with modern relativity. Let's look at one more important situation to drive this home. Here we have two objects with negative charges moving to the left. Electrically, they repel each other. Magnetically, they attract each other. It's worth talking about the sum of these two forces. There are three possible scenarios. Let's look at the free body diagrams. If the electrical forces are bigger than the magnetic forces, the objects will repel each other. If the magnetic forces are bigger than the electrical forces, the objects will attract each other. But what if they match? This would imply that we could not tell the difference between electricity and magnetism. When does that happen? If these two forces balance, they are equal to each other and their ratio is 1. We can put in expressions for the forces in this situation. Lots of things cancel out. The big Q's, the little q's, the r's. What we are left with is this. 1 equals the electricity coupling constant divided by the magnetic coupling constant times the square of the relative velocity. At a certain value of v, the electrical force and the magnetic force will match. Putting in the values for E and M yields the following. V squared is 9 times 10 to the 16 meters squared per second squared. Solving for v by taking the square root gives us a speed of 3 times 10 to the 8 meters per second. This is the speed of light. When you're traveling at the speed of light, electricity and magnetism are the same thing. At the end of the 1800s, there were a bunch of physicists studying electricity. There was a totally separate group of physicists studying magnetism. There was a totally different group studying light. This new insight caused them to realize they were all studying the same thing. Whether you're talking about a star, a light bulb, or a candle, all light is made in the exact same way. All light comes from atoms when an electron in a high bleacher falls to a lower bleacher. That transition represents a small electric current. That current will create a magnetic bubble. As that magnetic bubble comes in and out of existence, it will create an electric bubble. As that electric bubble comes in and out of existence, it will make a new magnetic bubble. This will keep happening. The rate at which these bubbles leapfrog through space is 300 million meters per second. This is the speed of light. We will spend our last few weeks of this course talking about light.